Alright, this is 2-1, Operations with Polynomials, and our objective here today is that we review about how to add and subtract polynomials and then also learn how to multiply them. So hopefully some of this will feel like familiar from previously, but we're going to learn some new things too, and it'll be a good review. So first of all, let's talk about some definitions and some words, vocabulary to talk about polynomials. First is a term, and a term is a single number or variable, or several multiplied together. It's a very broad definition because it can be a lot of different things, but we'll get used to what a term is here in a second. So a monomial is a polynomial with only a single term, with one term. So an example might be 7x squared. Notice that this is a single term. It might be easier to talk about this once we've seen something with more than one term. For example, a binomial has two terms, and this will look like x minus 4 or something similar. And these are both different terms. So what separates terms is adding or subtracting. Everything multiplied together becomes a single term, but adding and subtracting separates them. So a trinomial, as you might have guessed, has 3 terms and can look something like 5x squared plus 3x plus 2. Notice that we have 1, 2, 3 terms separated by adding in this case. Another important definition is the degree of a polynomial, and the degree of a polynomial is the highest power that the polynomial contains. The highest power that a polynomial contains. So if we look back at our example of a trinomial, this example, we're looking for the highest power of x, or whatever the variable is. We're looking for the highest power that it has. So in this case, it has a power of 2 on the 5x squared, and no other power is bigger than that in this polynomial. So this polynomial would have a degree, and I'll write this, it'll have a degree 2. The binomial example here has only x, and the power on that x, like sort of the assumed or the invisible power there, is that it's a single, like it's a single x, right? X to the first power, there's an invisible first power there. And so the degree of this polynomial is just 1, because there's no higher power. Monomial, this monomial here that we use to, as an example, has a degree of 2, because that is the highest power of x that it has. Okay, so let's talk about adding and subtracting polynomials. So the first thing we need to do to figure out adding and subtracting polynomials is what it means to be a like term, because like terms can be combined and unlike terms cannot be. So we have to get really used to this idea of like terms. So like terms are terms with the same variable, and if they have more than one variable, they have to have all of the same. So I'm going to put parentheses s, same variables, possibly, raised to the same powers. The same variables raised to the same powers. So the number doesn't matter, like if there's like a multiplied number in the front, that doesn't matter. What we need is the same variables raised to the same power. So this down here is sort of an exercise in how to recognize like terms. So we're sort of putting each of these in a separate category according to what term what other terms match it, right? So I'm just going to do one of these examples here. Just the notes below this video should have the rest of them in case you're curious. But I would actually prefer if you tried this on your own first. So what I'm going to do is start with this term right here, negative 2x squared. That's the term that I just put in there. And I'm going to look for all of the like terms in here. So what I'm looking for is all of the terms with x raised to the same power, which is squared. All of the terms with the same variable raised to the same power. So as I go through here, I'm looking, I see that this 3x squared also has an x squared and nothing else. And we scroll down the line. Let's talk about this one for a second. This one says 4x squared y. That is not considered a like term to what we already have because it has a y. Like even though it has the same variable to the same power, it has an extra variable, and we can't really do that. That's not allowed. So we even though it has an x squared, that would go in a different category with all of the ones with an x squared y. So let's keep going. I'm scrolling slowly through here. Okay, let's talk about this one. 25xx. So this is just written a different way, but that is still 25x squared. And that goes in the same category here. Even though it's written differently, that is still 25, and the variable is x, and the power is 2. And the only other thing I think that we're missing here is 20x squared. This one right here. That one is also a like term to everything that we've had there. So my encouragement to you is to go through each of these terms and put them in groups according to their like terms. I'm also gonna just tell you that this actually requires an extra one more category than I gave you here. So there's actually 1, 2, 3, 4, 5, 6, 7, 8 different groups of like terms that you can make out of this table. So I would encourage you to try that. Next page, we're gonna just do an example of adding these two polynomials. So notice that we have like this polynomial in parentheses. The parentheses are not super necessary here, and we'll talk about more why later. But we have two polynomials that are added together. So first thing I'm going to do is get rid of the parentheses because I don't super need them. The only reason that you'll ever need parentheses is if you're distributing something. So either distributing a negative, which we'll talk about in a second with subtraction, or you're distributing a number. Here we only have a plus in front of our parentheses, and that does not do anything when we distribute it. So we don't really distribute adding. So without the parentheses, this looks like 2x to the third power minus 5x squared plus 3x minus 9 plus x to the third power plus 6x squared plus 11. Now what we're looking for is like terms that can be combined. So the first thing I'm noticing is that this 2x to the third power can be combined with the plus 1x to the third power, which makes a total of 3x to the third power. And once I've done this, because this polynomial addition ends up being super long sometimes, I like to cross out the ones that I've already added so that I know what I have left at the end. So I just cross those out. And then we have negative 5x squared can be combined with this 6x squared. Again, because the variables are the same and the powers are the same. So same variable raised to the same power. So that is a negative 5 plus 6, which makes just a positive 1x squared, which I'll just write as a plus x squared because we don't need the 1 on there, it's implied. And then I'll cross those out. The last thing I'm noticing that can be combined, and let me grab a new color here, is this negative 9 and this plus 11. Those are also like terms because they have no variables raised to no powers. So they're just normal numbers that we're adding together. And Okay, so negative 9 plus 11 makes 2, plus 2. And I left a little space because I know that this 3x, doesn't have anything to combine with, so I'm going to just put that right here. The way that we like to write polynomials, and this is a good time to talk about this, the way that we like to write polynomials is by the highest power down to the lowest power. So in like descending order is what we call them. So we wrote this with the power of 3, the power of 2, the power of 1, and then no power at all. And that's normally how we like to write polynomials. Other orders are technically correct, but they're just easier to read when they're in order like this. The other thing that I want to note here, just to practice our vocabulary, is that the degree of this polynomial that we just added together is 3, because that is the highest power of x that we have in this polynomial, so the degree is 3. I am going to let you do this second example on your own or with the help of the notes. And let's talk about subtraction. So with subtracting polynomials, we will need to distribute a negative. And this is honestly something that everyone forgets to do, and so this is a really good thing to practice. So what we're going to do is sort of do an exercise in like a word problem, which I know everybody groans with word problems, but this is to help us recognize the need to distribute a negative. So this is my scenario. We have 10 apples and 6 peaches in a grocery bag. Your brother steals 2 apples and 1 peach. We already know, because we do that math in our head, that that should give you 8 apples because he stole 2 of our 10, and 5 peaches because he stole 1 of our peaches, right? But this can be represented as with polynomials. So notice that I have on this side here, it says 10a plus 6p. That I'm saying is 10 apples and 6 peaches. I'm just representing my word problem in a polynomial subtraction. And then he takes, that's what this minus, he takes, and then on this side we have 2 apples and a single peach. So same scenario, just represented with polynomials. And so what I'm going to do is I'm going to show you the wrong way first. If we didn't distribute that negative, let me get a red marker. If we didn't distribute that negative, we would start with 10a plus 6p minus 2a plus p. So I didn't distribute the negative, all I did was take away the parentheses in this wrong example. And then we would combine like terms, so I have a 10a and a minus 2a, so that gives me 8a, and then we have a 6p, let's cancel those, and then we have 6p plus another p makes 7p. So this subtraction problem gave us the answer of 8 apples, good so far, and 7 peaches. That's false, right? We already know that we should have 5 peaches left because he took 1 of our 6. How come we ended up with 7? Well, the answer is we didn't distribute the negative. That is a completely necessary part. It doesn't make any sense for us to not distribute that negative because we end up with adding where we shouldn't be adding. So let's do this the right way. Let's distribute the negative. Hang on. Whoops. 10a plus 6p minus, and then I'm just going to keep the parentheses for a second so I can visualize how I'm distributing. I'm going to distribute that negative to both the 2a and the p. So, there we go. So we end up with 10a plus 6p minus 2a minus p because that negative got distributed in both of those terms. And now when we combine like terms, we end up with 8 apples again, and then 6p minus p, which gives us the 5p that we needed, the 5 peaches. This reads 8 apples and 5 peaches. So something that we know intuitively in a word problem or an actual real life situation doesn't always translate into seeing that as math problems and being able to know to distribute the negative. But just remember this scenario whenever you're thinking, okay, what do I do with the negative? Please distribute it. It goes to everything in the parentheses. And then you'll end up with an answer that makes sense. So that was our little exercise. And I'm going to do one example of this one. And just to mix things up, I'm going to do number 2 instead of number 1. So first thing, and in case you're curious, I am not distributing the negative. The negative does not distribute backwards like this. So the reason I'm just taking the parentheses off the first polynomial is because the negative only needs to be distributed into the thing that follows it. So just like up here, we take 2 apples and a peach. We're taking away 5z squared and negative z and 3. It doesn't need to be distributed backwards. That doesn't read like English. So we're going to distribute this negative into each term. We have 3 terms in there, into each term of this polynomial. So I'm going to start with a minus 5z squared. And then this z is already negative, and so when we distribute that negative, it turns positive. Positive z. And then this positive 3 becomes a minus 3. So if it helps you in this process, distributing a negative just flips every single operation here. So we flipped the positive 5z, we flipped the negative z, we flipped the positive 3. There you go. And then we're going to combine like terms. So we have 4z squared up here and negative 5z squared right there, which gives us a negative 1z squared. Or actually, let me just write that as negative z squared because we don't need the number there. Got those. And then we have plus 9z plus z, these two, gives us 10z's. And then we have a minus 12 minus 3, which gives us minus 15 at the end there. So this is our final answer. Hopefully that helps a little bit. Just remember to distribute the negative or else you're going to get a nonsense answer, something that does not make sense. Again, please get these other examples from the notes. And now we come to multiplying polynomials. So this is something that might be new, probably is new to you, and so this is where I want to spend the most time and effort here, because this is going to be something that is absolutely essential for your life for the rest of your math career, being able to multiply polynomials. So we are starting with this example of 2x minus 5 times x plus 3, and to multiply polynomials, the rule is that every term in the first polynomial gets multiplied with every term in the second polynomial. So there's a lot of different ways to organize multiplying polynomials. Some people use like boxes, some people use just lines, some people use distribution method. So I am going to teach you the way that I feel is the most, I just prefer it. This is the way that I do it. But if you're curious about a different method or a different way to organize this math, I can certainly teach you the other ways. The rule, though, as long as, I don't care how you organize your math, just that every term in the first polynomial gets multiplied with every term in the second polynomial. This is just distribution, and I'll talk about that in just a second. But first I just want to show you. So here I have 2x and negative 5. And so in order to be sure that every term in the first polynomial gets multiplied with every term in the second, I'm just going to go term by term. So I'm going to take my 2x and multiply it by everything in the second polynomial, the x and the 3. So mathematically that's going to look like 2x times x plus 2x times 3. So here's my first term getting multiplied with everything in the second term, the second polynomial. And now we have the 5. I need to make sure the negative 5 also gets multiplied by everything in the second polynomial. So I'm going to do sort of the same thing here. I'm going to multiply the negative 5 by everything in the second polynomial, which gives me this math. I have negative 5 times x plus, actually I'm going to delete that plus because it's going to be a minus because I'm minusing 5, or multiplying by negative 5. Here we go. So we have negative 5 getting multiplied by the x and the 3. So notice that we now have every term in the first polynomial multiplied by every term in the second polynomial. These lines that I drew, this is the method that I use and I really like. People call it like the rainbow method or something, just because you draw like curved lines to connect things, but this helps me to visualize distribution. Because notice this is the same thing that we do for distribution, it's just one more level. Like if we forget that this 2x is even there, this distribution that we do with the negative 5 looks exactly like normal distribution. We are just multiplying that negative 5 by everything in the parentheses. So this really is just distribution. It's just like double distribution, essentially. So we're just doing it twice. So if that helps you remember how to do this, that's great. So I'm gonna go down here and finish my problem before I keep talking. I'm gonna just multiply each of these things that we wrote out so that we can see what's happening. So the first I have 2x times another x, which gives me 2x to the second power. And then I have 2x times 3, which is 6 x's. And then we have minus 5x. That just looks like minus 5x. And then we have a minus 5 times 3, which is a negative 15. And the very last thing to do here is to just combine like terms. So these middle two terms, often when you're multiplying two polynomials, your middle two terms will be able to combine. Sometimes it's more than that, but just watch for things that can combine. So 6x minus 5x just gives you a single x, and everything else stays the same. And that is our answer. That's how we multiply polynomials. So this is just a reminder down here that distribution, we're just distributing two separate terms into our parentheses instead of a single term. So normally we have, like this problem, we have 2 distributed into x plus 3. Let me do some highlighting. 2 distributed into x plus 3. So we're really, truly doing the exact same thing. So let me just illustrate to you another way to sort of visualize distribution. So you are just distributing twice. First you distribute this negative 5, and you can get negative 5x. We already did this math, so I'm just speeding to where I already know the answer because we just did it. And here's our second term. We're just going to distribute the second term into the parentheses. And that gives us the 2x squared and the 6x. So truly it's just distribution. It's just doing another set of distribution. Just if you remember nothing else, just remember this rule up here, that every term in the first polynomial gets multiplied with every term in the second polynomial. So I like to use these lines, and I do it on the top and the bottom just so that I don't get this like mixed up rainbow situation going on, but I don't care how you do it, as long as you're organizing it in a way that you can understand. So we're going to do a couple examples on this one because this is more of the new material, and I want to be able to show you some things here. So let us distribute this 3x squared into the parentheses. In this situation, there is only one term, so this works just like normal distribution. The reason I put this example on here, though, is because we have sort of high powers of x happening, and I want to make sure that we know how to deal with those. So 3x squared times 5x plus 3x squared times 7. So notice that I'm distributing this 3x squared in to multiply with both of those things. And then we multiply. So 3x squared times 5x. The 3 times 5 just gives us 15. And then we have an x squared times another x, which gives us x to the third power. So just remember your exponent rules on there. And then we have 3x squared times 7, and the only thing we have to multiply is the 3 and the 7. So that's 21x squared. And that's as far as we can go with that one. Because that's an x squared and an x to the third power, and those don't combine because they are not like terms. They are not the same power. Let's try number 2. So we are going to take, this is our first example of 2 things to distribute. So I'm going to distribute the negative 2 and the x. So just following along with my lines here, I have x times the x from inside the parentheses, the other parentheses. I guess I should say the second parentheses to make it super clear. And then we have the x times the 6 from the second parentheses. And then we have the second thing to distribute, which is the negative 2. So that first multiplication gives me negative 2 times x. And then we have negative 2 times 6 last. Let's highlight really quickly just so we for sure see. So I just followed my lines and distributed both the x and the negative 2 into the second parentheses. So now we just multiply. We have x times x, which gives us x squared, and 6 times x, which gives us 6x. And then we have negative 2 times x, which is just minus 2x, and then negative 2 times 6 gives us minus 12. And these two things can combine. Like I said, it's pretty normal for the middle two to be able to combine, but just be careful and watch for like terms. So 6 minus 2 gives us 4x, and this is what we have left. X squared plus 4x minus 12. And because I know some of you will wonder, multiplication, just like we learned in our 1-3 lesson where we talked about the properties of real numbers, multiplication is commutative, which means that it doesn't matter which order we multiply in. And so if you ever wanted to try it, you can try one of these problems in reverse. So you can put like x plus 6 in front of x minus 2 and see if you get the same answer. I'll spoil it for you. You will get the same answer. And it's because of that rule that everything in the first gets multiplied with everything in the second. It just ends up being in the slightly different order before you combine things, but your answer will be the same. So it doesn't actually matter which direction you're multiplying these. You could be multiplying x plus 6 times x minus 2, or what we have on our paper, and you'll get the same answer because multiplication is commutative. So don't ever get stumped by, okay, I don't know which one to distribute into which one. Just do one way and you'll get it right. Number 3 is kind of peculiar. So we have just x minus 4 parentheses to the second power. And I want to bring up this one because I know that you'll see this in your life. You might be tempted to do something like, and I'll write this in red just so we know, to do something like this, where you just give the power to both things in the parentheses, because that was the rule that we learned for if you have a product to a power, like something like 3x squared, you give the squared to both the 3 and the x. This is true. But if you have subtraction or addition in the middle here, this rule is not, that rule that we learned does not apply to things that are added together. It's only things that are multiplied. Again, multiplication and powers work really well, and so do division and powers. But adding and subtracting and powers don't play well together. You can't just distribute the squared in there. What it actually means So that's the wrong way to do it. What this actually says here is that we have two x minus 4s multiplied together. Just like when we were writing things out to illustrate power rules, or exponent rules, I should say. If we just write this out, we end up with x minus 4 multiplied by itself. And we need to distribute this. This is absolutely a situation where we need to distribute. Yeah. So let us distribute here. I am not using the right, there we go. I'm going to distribute the x in there, and then the 4. I switched colors slightly. It's okay. So we have an x times our x from the other parentheses plus, oh, we have a minus x times the 4. The reason we have a minus is because it's negative 4. So really we're doing x times negative 4 here. And then we have the other distribution. We have a negative 4 times x. And then the last bit here is negative 4 times negative 4, which I am just going to write as 16. Hopefully you know what this means. Actually, I lied. I'm not going to do that. We'll just do minus 4 times minus 4. There we go. Okay. X times x gives us x squared, and then we have minus 4x, and then minus 4x again, and then plus 16. These center two will combine. Negative 4 minus 4 gives us 8x. And that's our answer. X squared minus 8x plus 16. So just be careful on those ones. Please don't just give everything inside the thing like the power like this. It's a good idea, but it's wrong. It only works if it's multiplied inside, and these are subtracted, or adding also would be the same situation. So what this is saying is this. 2x minus 4 is multiplied together. Okay. There's a bunch more examples. I'm going to leave that to you to do, except for I want to do number 3 because it has an extra thing, and I want to make sure we know how to do that. So on this one we have like a 2 in front of the parentheses, and then an x minus 5, and then a 3x plus 7. So what I'm going to do is I'm just going to distribute this 2 first and ignore everything else. I'm going to distribute that in there first, and that gives me 2x minus 10, put it in parentheses, times 3x plus 7. And here we've just solved our problem. Now we only have 2 things to distribute, which we are super used to. So I'm going to distribute the negative 10 and the 2x. There we go. So we have 2x times 3x, then 2x times 7, then negative 10 times 3x, then negative 10 times 7. And 2x times 3x is 6, and x squared, because there's 2 x's multiplied together. Be careful about that one. When you're multiplying, the power can change. When you're adding, it's not. Then 7 times 2x is 14 x's, and negative 10 times 3x gives us negative 30x, and negative 10 times 7 is minus 70. So last step here, these middle two combine, and that gives us negative 16x. And that's our final answer. So the moral of the story is here, if you have like an extra thing happening, you just distribute one at a time. So the thing that I would say not to do is don't distribute that 2 into both of the parentheses, just into one, because you'll end up with like a lot of extra 2's if you distribute into like both parentheses. It's just like if we're doing a math problem like 4 times 6 times 2. you don't distribute this 4 into both of those things because everything's multiplied, so it doesn't need to be distributed. So this situation is just like what we have down there, except for that each of these is a polynomial. So don't distribute it into both parentheses. You can just do this multiplication problem, which is 24, and then do 24, then do this multiplication, which is 48. So that's my spiel on that. So last thing I want to talk about is that this gives us the power, this multiplying polynomials gives us the ability to multiply complex numbers. So I know that we don't love these and it's coming back to haunt us. But that's okay. We're gonna multiply these complex numbers together just using the same rules that we just learned of distributing things into the parentheses. So I'm gonna distribute the 2i and the 12 into the other complex number. So we have the 12 times the 12 from the other parentheses, and then a minus 12 times 2i, and then plus 2i times the 12, and then plus 2i times negative 2i. I ran out of room because I was writing too big. Okay, not the prettiest one I've ever done. That's okay. Okay, so 12 times 12 is 144. You can check me on a calculator on that. And then negative 12 times 2i would give us negative 24i. And then 2i times 12 is the same thing, but it's positive 24i. And then positive 2i times negative 2i is actually minus 4 times I squared. So the weird thing about multiplying imaginary or complex numbers together is you end up with powers of I. So you just have to remember your powers of I rules from when we learned that in 1-4. This I squared is actually equal to negative 1. Hang on, let's write the whole thing. 24i. Oh, I'm going to do one more thing actually on this step. I'm going to combine these middle two. Again, the middle two combine. And believe it or not, that's a negative 24i plus positive 24i, which actually gives you 0, gives you nothing in the middle. So I'm just going to write that for now just so we remember what happened there and why it's empty. And then in the next step, we don't have to write them that 0i because it's nothing. So 144 and then minus 4 times negative 1 is positive 4. Get ready for this. 144 plus 4 is just 148. So we did that complicated complex number multiplication situation and we got a normal number. So kind of cool actually, and it's just using the rule that we just learned, multiplying polynomials, and just this power of I thing from last unit. So I think it's pretty cool. This is a situation where we have imaginary numbers as kind of a bridge between the problem and an answer that's real. So something that is cool about this, these two complex numbers, 12 plus 2i and 12 minus 2i, we call these conjugates. Let me make sure I'm spelling that right. No, I wasn't. Conjugates. Conjugates, when you multiply them together, the imaginary part disappears. And the way that you get conjugates is that you just, it's just this little piece that changes. So essentially it's the same complex number, but the operation or the sign in front of the I part, the imaginary part, is opposite. So I'm going to write that down here because I think that comes up in your homework. The complex conjugate that's what they're called, is the same complex number except the imaginary part is the opposite sign. The imaginary part has the opposite sign. So some examples of complex conjugates, like if you have 3 minus 4i, the complex conjugate would be 3 plus 4i. The complex conjugate of negative 2 plus 10i is negative 2 minus 10i. So all I'm changing here is the sign in front of the imaginary part. So that's just a fun concept from complex numbers that we didn't get to learn because we didn't know how to multiply polynomials yet. So that's all I'm going to do for you today. Don't worry about these two last examples with complex numbers. I'm not super worried about that for your homework or for your future. The most important is just to get this multiplying polynomials down, just the ones with normal variables. And just to sort of understand the concept of complex conjugate, I think there's like one question on your homework about that. So that's all I have for you.